I am Neeta Sharma from PM Expert, and today I'll explain gradient descent in a simple, step-by-step way. Think of gradient descent like walking down a hill in fog. You cannot see the whole hill, so you take small steps in the direction that goes most downhill again and again until you reach the valley. In machine learning, the hill is the cost function, a number that measures how wrong our model is. Our goal is to make that number as small as possible. For linear regression, a common choice is the mean squared error. J of theta equals 1 over 2m times the sum over I of the prediction minus the target squared. To know which way is downhill, we compute the gradient. It tells us the slope with respect to each parameter. For linear regression with features x, the partial derivative of j with respect to theta sub j equals 1 over m times the sum over I of prediction minus target times x sub j. Collecting all partial derivatives gives the gradient vector. The update rule takes a small step opposite the gradient, which moves us downhill. Theta sub j becomes theta sub j minus alpha times the partial derivative of j with respect to theta sub j. Alpha is the learning rate. If alpha is too big, we overshoot. If alpha is too small, we move very slowly. Now, watch a few steps on our valley. Let us compare two learning rates on the same valley. With a small alpha, steps are safe but slow. With a large alpha, steps jump across the valley and may oscillate or even diverge. Let us put it all together. 1. Initialize theta, often to zeros. 2. Repeat until convergence. Compute the gradient of j with respect to theta. 3. Update each parameter using theta equals theta minus alpha times the gradient. 4. Stop when j stops decreasing. Finally, here is a two-parameter picture. The curves are contour lines of equal cost. The gradient points perpendicular to these lines. Downhill, gradient descent follows a path that zigzags toward the minimum as we repeat the update rule. Recap. The cost tells us how wrong the model is. The gradient tells the slope and the best local direction to reduce the cost. Gradient descent repeats small steps downhill until we reach the minimum.